My pleasure to introduce Jessica Sidman. Um, Jessica got her PhD from University of Michigan under the supervision of Robert Lazarsfeld, then did an NSF postdoc split between Berkeley and UMass Amherst. Went to Holyoke as a tenure track position, ran through all the ranks up to professor, and has moved relatively recently in the same town to Amherst College to be a professor there. Jessica's going to tell us about Terracini secants and matroids. I forget the exact title. I apologize, Jessica.
Terracini matroids, yeah.
Yes,
So
go
thank
ahead.
you all for coming, and for the invitation to speak. I'm going to speak about a project that was joint with Fatemah Mohammadi and Louis Theran. And I want to start with the motivation for the questions that we were asking and answering. And so the motivation is a very geometric question. So the question I want us to think about at the beginning of the talk is how independent are the distances among n points in Euclidean D space. So for example, I might be thinking about 4 points in the plane, and suppose they are like x1, x2, um, x3, and x4. And suppose I know the following distances. Like I know the distance between x1 and x2, x1 and x4, x3 and x4, and x2 and x3. And I'm going to let Eij denote the squared distance between points I and j. And so, of course, if I know these 4 distances, then there are infinitely many choices, so infinitely many possibilities for, say, the diagonal distance E13. There are infinitely many choices for that, and for E24. But if E13 is fixed, then we only have 2 choices for the other distance, E24. Okay, so like that's the very concrete version of this question. And you might say, well, so like in what sense do you mean independent? And I want to consider algebraic independence. So we, for this talk, will consider algebraic independence. And let me introduce the setting that I want to work in. So for this talk, let's let X be an irreducible affine variety of dimension R in some affine space A to the N. And let's let E be the set of coordinate functions on AN so that the ideal of X is going to be contained in the polynomial ring generated by those indeterminates in E. Okay, so I want to define the algebraic matroid for you. Its ground set is the set E, and then I'm going to define a bunch of sets that I'll call its independent sets. And these are subsets of the indeterminates with the property that if I intersect the ideal with the polynomial ring generated by the variables in my subset, I get the 0 ideal. Okay, and so I'm going to denote by m of x So this is the set E and these independent sets I, and this is the algebraic matroid of the variety X. And again, these are the independent sets in the matroid. So if you're an algebraic geometer, like I want to spend a little time thinking about like for when is this an interesting question at all? And what kind of like what properties of a variety does this pick up? And so let me just do two very simple examples so that like you sort of get in your head what's going on here. So for example, if I take X to be a plane, say in C3, and its ideal, say, is just generated by setting Z1 equal to 0 in the polynomial ring C adjoined Z1, Z2, Z3, then if I wanted to think about the maximal independent sets of the algebraic matroid, well, there's only one of them. So the maximal independent sets of the algebraic matroid of this variety consists of just the set containing the two indeterminates Z2 and Z3, right? But just to get a sense of what's going on here, if instead I took the ideal of a variety to be, say, the ideal generated by, I don't know, Z1 plus Z2 minus 5 Z3, again, contained in the same polynomial ring, Z1, Z2, Z3. Well, then, if I think about what are the maximal independent sets of the algebraic matroid, now the maximal independent sets have the same size, but there are many more of them. So for example, Z1, Z2 is a maximal independent set. Z1, Z3 is a maximal independent set. And Z2, Z3 is a maximal independent set. And so that is really the uniform matroid of rank 2 on 3 elements. So it's sort of like combinatorially, it's like completely, it's the most uninteresting matroid of rank 2, so where the maximal independent sets have size 2 on 3 elements. So the other one, the first one, is sort of more interesting. Not all of the 2-element sets, subsets of variables, are independent. So it tells you something is going on. And the thing it tells you that's going on is that your variety has special, like the coordinates are kind of special. The equations are special, right? It's defined by a monomial instead of something that's sort of a more generic linear form. And so what I want you to remember about algebraic matroids then is that this sort of mantra that algebraic matroids are interesting, I think, are interesting if either your coordinates are somehow special. And so in the first example, the coordinates were special because the ideal was generated by monomials, so the coordinates are sparse in some sense in the equations, or if the coordinates in your ring have some kind of interpretation that you care about. Okay. Oh, and just the other thing I wanted to mention before we move on is that here, the rank of an algebraic matroid, that's the size of its maximal independent sets, is always going to be the dimension of the variety. Okay, so this is the size of a maximal independent set. All right, so let me return to my motivating question, and this is a the algebraic matroid that I will help us think about algebraically independent distances is both I feel like the coordinates are special and they have an interesting interpretation. So for this example, we're going to fix D, which is the dimension of the ambient space, and N, which is the number of points. And then we'll define the ground set of the matroid, which is the set of indeterminates of the polynomial ring, to be Eij, where I and j, so there are n choose 2 of these guys. And I'm going to define a map of polynomial rings from C adjoined those n choose 2 variables to C adjoined the coordinates of x1, x2, dot, 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 through xn. So this ring has dn variables. And the map will send Eij to the polynomials, the quadratic forms that I get if I look at the squared distances. So it'll look like x I1 minus x j1 squared plus dot 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 through x j, no, xin minus xjn quantity squared. Okay. And so what's the
Could
kernel
that
of
be a
that?
D? Are there, D coordinates for our vectors or
Oh, you're right. D coordinates. Yeah. There are endpoints, D coordinates. Thank you. All right. Greg's paying attention. Awesome. All right. So the kernel of this ring map is what I'll call IDN. And this is precisely the ideal of polynomial relations on the squared distances among endpoints in R to the D. So I could have taken this ideal, like it doesn't matter whether I look at the kernel of this map over R or over C, but for later in the talk, I'll need to be working over a field, algebraically closed field of characteristic 0. So let's just work over C from the get-go. So what do we know about this ideal? This ideal, it's a prime. So this is prime. And it's also homogeneous. Its variety, so the V of this ideal, is what Borcha called the Cayley-Menger variety. So this is the Cayley-Menger variety. And it was introduced by Borcha, who wrote a really lovely paper with a ton of algebraic geometry in it. It was never published. There's a shorter version of the paper was published that really got to the stuff that the people in rigidity theory who sort of do distance geometry cared about. But it was a really beautiful, there was really beautiful algebraic geometry in that paper. And we'll denote this variety by CMDN. So that's the Cayley-Menger variety of endpoints in R to the D. If you want to think about it concretely, IDN is generated by the D plus 1 by D plus 1 minors of an n minus 1 by n minus 1 gram matrix. What does that look like? Well, it's a symmetric matrix. On the diagonal, I have entries that look like 2e, 1n, dot 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 through 2e n minus 1n. And on the off diagonals, like the first entry here, I would have e1n plus e2n minus e12. And you could sort of fill in the rest. It's symmetric. Okay. So that's the Cayley-Menger variety. And the independent sets of the algebraic matroid of this variety are exactly the algebraically independent distances or squared distances among n points in R to the D. And so here, if you want, you could even draw these independent sets as graphs, for example. So like if we had D equals 2 and N equals 5, if I wanted to draw an independent set, one of the independent sets, so here would look like this. So, oh, that's supposed to be a line, sorry. And so that's maybe 3, 4, 5, where this is like E1, 4, etc. So that's one independent set. Up to graph isomorphism, there are exactly 3 maximal independent sets. So this is a maximal independent set. So hopefully I've convinced you that the first question I asked, which was what are the algebraically independent distances, is really a question about what are the independent sets of an algebraic matroid. And now I want to try to convince you that this is also a question about secant varieties. But before I do that, actually, there's one more example. Oh, actually, I want to say a little bit more about matroids and algebraic matroids before I do that. So there's another example that's near and dear to anyone who does any algebraic geometry or commutative algebra, and will play an important role later in the talk. So suppose I have the Veronese embedding of P2 into P5, and maybe I'll think about that as a toric variety. So as associated to these 6 lattice points in the plane, where if I think about like dehomogenizing the coordinates on P2, then I have sort of 1s, not t, s squared, t squared, and st. And I can associate those to the coordinates of P5. So I'm going to do it this way. So it's Z1, Z2, Z3, Z4, Z5, Z6. And then I'm going to define a matrix A. So it's a 3 by 3 symmetric matrix, Z1, Z2, Z3, Z2, Z4, Z5, Z3, Z5, Z6. Okay, so I'm going to let X be the like the affine cone over the affine cone over the image of P2. And so this will be in affine in A6. And the ideal of X is generated by the 2 by 2 minors of A. And because this is a toric variety, and so the equations of a toric variety, the generators of the ideal of a toric variety are really sparse. And so those are coordinates that are special. And so if you're thinking about this paradigm that an algebraic matroid is going to be interesting if the if the coordinates are special or the interpretation is interesting. So here we have a coordinates are special situation. So we shouldn't expect that we get like a uniform matroid. And so what do we get? Well, remember, as an affine variety, the dimension of x is equal to 3. So we should expect our maximal independent sets to have size 3. And for example, here are some maximal independent sets. Here are a couple of them. So one is the set Z2, Z3, Z5. Z2, Z3, Z5. I'll highlight that for you in the matrix. So Z2, Z3, Z5. And in the lattice, if you're a toric person, it's those three, corresponds to those three lattice points. And then another maximal independent set, for example, corresponds to these other three that I didn't choose. So Z1, Z4, Z6. So those are two maximal independent sets. Z1, Z4, Z6. Okay. But not all 3-element sets are independent. For example, the following set is dependent. The set Z1, Z2, Z4, and that's dependent because, is this right? Oh no, that's not the right thing. I'm trying to find my pointer. There it is. That's dependent because this 2x2 minor is supported only on the variables Z1, Z2, Z4. So that's in the ideal. So if I intersect the ideal of X with the ring generated by Z1, Z2, and Z4, I won't have a non-zero intersection. So that set isn't independent, it's dependent. Okay. Let me tell you a little bit more about matroids. So I haven't told you anything about the axioms for matroids. So in general, what is a matroid? So if I have some set E, and then I'm going to define a set of independent sets. So these are subsets of the power set of E satisfying 3 axioms. One is that the empty set has to be independent. 2 is that if I is an independent set, then all the subsets, so the power set of I has to also, all those subsets have to be independent as well. And the third is that if I have 2 independent sets and one is bigger than the other, oops. So if I2 has more elements than I1, then there exists an element in I2 but not I1 such that if I take I1 and I throw that element E into it, that's also an independent set. And so this M equals E, the pair EI is matroid. And so matroids were first defined, I think, by Whitney in like the 1930s to axiomatize simultaneously linear independence in vector spaces and acyclicity in graphs. So those satisfy all the axioms of a matroid. And one thing, if you look at like van der Waerden, the first and second edition of van der Waerden, you can see that in between that, people sort of discovered that algebraic independence over a field satisfied these axioms as well. So there are lots of cool matroids in the world. Let me just tell you quickly what a linear matroid is. So if V is some vector space and E for us, let's take it to be a finite collection of vectors in V, then, the pair EI is a matroid, where the set I is exactly the set of all linearly independent subsets of this set E. And so, fun fact, there are matroids that are algebraic. So the way I've set it up, that can be sort of realized as the matroid, algebraic matroid of a variety, but not linear. And however, if you're working over an algebraically closed field of characteristic 0, we can say something more. So there's a theorem of Ingleton saying that, so if K is algebraically closed and the characteristic of K is 0, and I have some variety in A and K, then this algebraic matroid, so the algebraic matroid of the variety, is going to have a linear representation. And I just want to say a couple of words about how this works, because this is actually sort of a key part of the proof of our main theorem. So what's the idea? If I had what's the idea? If I had an algebraic matroid, how would I get a linear one? So in its most sort of concrete form, the idea is, well, if I have a polynomial in the ideal of x, what can I do? I can look at its differential. And that, at a point of my variety, is going to give me a linear relation on the differentials of the coordinates. So at a point of x. So, for example, right, if I had maybe that 2 by 2 minor z1, z4 minus z2 squared, and I looked at its differential, then I get, of course, z4 dz1 plus z1 dz4 minus 2 z2 dz2, right? So at a sufficiently general point of my variety, I'll get a linear relation on dz1, dz4, and dz2. And then you can sort of see why you need both of these hypotheses on the field. If the field isn't algebraically closed, you might not be able to have any points to specialize at. And if the characteristic is P and you had pth powers in the generators of your ideal, then the supports can change when you take the differential. So you sort of need both things to be able to go from algebraic matroids to linear matroids. Okay, now we are finally at the point in the talk where I'm going to try to convince you that my original question was not only about algebraic matroids, it was also about secant varieties. So first, let me just remind people what a secant variety is. So definition. And here I'm going to work, I know people use secant varieties are projective, but we're going to work here over with affine varieties, and later in the talk it'll be affine varieties with homogeneous ideals. So I'm really thinking of working with projective varieties, but all of the like numerology will work out better if I think about affine dimension, and like it's the affine dimension of the variety that's the same as the rank of the algebraic matroid. So let's do this. So here I'm going to have I of x. Oh, let's have it just be homogeneous now. So homogeneous. And then I'll define its sth secant variety to be the Zariski closure of the set where I take s points in my variety and I add them together, and then I take this Zariski closure. And this is what I'll define to be the S secant variety of my original variety X. And I claim that then this Cayley-Menger variety is a secant variety, and it's the D secant variety of CM1N. And if you're not already convinced of that, I just want to scroll back to where I gave the measurement map. And so what you can see from the form of the measurement map, right, is that this is the sum of D one-dimensional distance, squared distances, essentially. Okay, so this is a secant variety. And then, so this is in this, oops, hold on, my lights. I was too still. My office decided to shut my lights off. So people in rigidity theory who study sort of distance geometry think about this a lot. And we were inspired by work of, so let me say, and so we were inspired by work of Cruikshank, Mohammadi, Nixon, and Tanagawa to ask the following question that generalizes the motivating question, which is, well, how is, or comes from that, how is the algebraic matroid of a secant variety related to the algebraic matroid of the original variety? And in particular, you could ask, well, how do these operations commute with one another? What if you take, secant varieties, and what could you do? If you wanted to find the algebraic matroid of the secant variety, is there something you could do to the algebraic matroid of the original variety to get it? So actually, I think that might be a good place for us to pause in between the two parts.
Sounds good. I've got 5 past the hour, so we'll resume at let's say 10 past the hour. I'll pause the recording.
Cool. Ready. Okay. So thank you for sticking with me. So to answer this question, I want to introduce one more definition from matroids to give us the language to talk about the answer. So definition, suppose I have two matroids now on the same ground set. So matroids on the same ground set E. I want to tell you what I mean by the union of the matroids. So the union of M and N is going to be a matroid with the ground set E and independent set I, where this new set of independent sets is going to consist of unions of the other ones. So unions I1, union I2, where I1 is independent in the first matroid and I2 is independent in the second matroid. Okay, and then I'll denote by SM to be the S-fold union of M with itself. So that's S of them. And then the final thing I want to say is that we say that the matroid M is less than or equal to the matroid N if every independent set in M is also independent in the matroid M. Okay, so what are some observations that we can make? The first observation is very simple, just that if I look at the algebraic matroid of some variety, then it's less than or equal to the algebraic matroid of its second secant variety, which is less than or equal to the algebraic matroid of its third secant variety, et cetera, until eventually, the matroid, the secant varieties will fill the ambient space, and then the matroid is sort of uninteresting. Okay. So our first main theorem is what we call the subunion theorem. And this is due to Fatemah, myself, and Louis Theran. That it says that then, so K here is algebraically closed and characteristic 0, then essentially the algebraic matroid of the S secant variety is less than or equal to the S-fold union of the algebraic matroid of the original variety. And just to say a few words to give you an idea of the proof, well, maybe it's no surprise if you work with secant varieties, we use something called Terracini's lemma, which essentially says that at a sufficiently general point of the secant variety, the tangent space is equal to the sum of the tangent spaces at the points that you've summed together. And so the idea then is that since we're in an algebraically closed field of characteristic 0, we can take our algebraic matroid and we can linearize it and then use Terracini's lemma and some linear algebra to get the result. And here we'll say that this algebraic matroid is a Terracini matroid, so is a Terracini matroid if equality holds. So, the algebraic matroid of the secant variety is equal to the S-fold union of the original algebraic matroid with itself. So we'll call that a Terracini matroid. Okay. So then the question is, so like I claim that actually when equality holds, that's like the non-interesting case. When you have interesting combinatorics, equality will fail. And you'll really want to know, so like what are the sets where equality fails and why does that happen? So let's think about when equality fails. So that's the question I want to think about now. When does equality fail to hold? Well, let's go back to that the example where I'm thinking about the Veronese embedding of P2 into P5. So let's see, what can we say about the rank of 2 times m of x? So remember, the rank of a matroid is going to be the size of a maximal independent set, and 2m of x is the union of m of x with itself. So its independent sets are unions of independent sets of the algebraic matroid of x. Now, if we go back to the example, what you see is that the green set, which is independent, so Z2, Z3, Z5, is disjoint from the purple set, which is independent, which is Z1, Z4, Z6. So basically this shows that if I take the union of those 2 independent sets, that is an independent set of 2 m of x, and it has size 6. And that's as big as it could get because I only have 6 variables. So this tells me that the rank of 2m of x is 6. But what we know from algebraic geometry, right, is that the dimension of the secant variety, well, we know that the secant variety is cut out by the determinant of that 3 by 3 symmetric matrix. So the affine, the dimension of like the affine cone over it is going to be 5. Okay, so this says that the rank of the algebraic matroid of this secant variety is equal to 5. So in this case, for the Veronese embedding of P2 into P5 by quadrics, the Terracini matroid property fails. And so let me give you a definition related to secant varieties that'll give me the language to sort of talk a little bit more about our next result. So here's a definition from secant variety land. If X is contained in AN and it has dimension R, and again, it has a homogeneous ideal. So really, I'm thinking this is the cone over projective variety. The expected dimension of the isthe secant variety is the minimum of S times R and the dimension of the ambient space. And I'm going to say that if the dimension of this secant variety is less than the expected dimension, we'll say that X is S defective. Okay, all right. So let's look at another example then. What if we look at the example where we take the Veronese embedding of P2 into P9 by cubics? Okay, so this is not a 2 defective it's not a 2 defective variety. Its secant variety has the dimension we expect. But let's take a look, let's see what happens. So I'm gonna think about this as a toric variety again. So now it's associated to this bigger lattice polygon. Did I get all the points? Does that look right? I think it's right. Am I missing a point? Wait a minute. 3, 1, 2, 3. There we are. Okay. So like here, the monomials are like 1s, s squared, s cubed, t, t squared, t cubed, st, s squared, t, and st squared. Okay. So this is not defective, I claim, but we can find 2 bases, maximal independent sets of the algebraic matroid of X, whose union is not independent in the algebraic matroid of the second secant variety. So I don't know, does anyone see where they are? What you can do? Essentially, the issue is that I have this like subtriangle here, for example. This is one of the bad things, right? So that is the set of lattice points that gives the quadratic embedding of P2 into P5, right? And my three independent, those three, the coordinates that correspond to those three monomials are still independent, and as are the coordinates that correspond to those three monomials, and still, so their union is an independent set in the union of the algebraic matroid of the original variety with itself, but it's not independent in the secant variety because the same equation, like that same determinant, that same 3 by 3 determinant, vanishes on these 6 coordinates. So this, though, can give you a hint at what the theorem is going to be. This is exactly sort of the obstruction that we have to avoid for equality. So theorem. Again, this is Fatemah Mohammadi, myself, and Louis Theran. So suppose now I have some variety x in C to the n, where it's defined by a homogeneous ideal. So I'm thinking projective. I also want it to be if you sort of think about it projectively, not a cone in I wrote Pn minus 1. I think that's right, Pn minus 1. I think that's what I wanted. And I want it to be non-degenerate, so have no linear forms that vanish on it. Then the algebraic matroid of the isth secant variety is equal to S times M of X. In other words, it's a Terracini matroid if and only if there does not exist a basis B, so a maximal independent set of the union matroid such that the projection from X to the coordinates indexed by B is S defective. Because that's exactly what was going on in this example. If I project the image of the Veronese embedding by cubics to these coordinates, I get a defective variety, and that's sort of preventing me from having the Terracini union property. So given that, you can try to think, so like what varieties are going to have this property or what varieties will fail to have this property? So for example, interestingly, like if you have a projective curve and you look at the secant variety of a projective curve, it always has the Terracini matroid property. And if you have like in generic coordinates, you expect a variety to have the Terracini matroid property. What varieties do we expect like might not have this property where there's something more interesting going on with the matroids? Well, varieties where the coordinates are maybe sparse and special. So for example, toric varieties. And so an observation that I want to make is that, like, let's just think about surfaces for a minute. Defective toric surfaces are rare, but defective projections of toric surfaces are very plentiful. So you can sort of see why that's true. So if you think about if P is a lattice polygon, and I'm going to get some projective toric surface from that lattice polygon if P contains that little triangle corresponding to the Veronese embedding of P2 into P5 by quadrics. As long as it contains that, then it has to be the case that the algebraic matroid that would correspond to like the toric variety that I get by embedding by those lattice monomials is not equal to 2m of xp, right? Because I could project onto the Veronese surface. So, I mean, as soon as you get like a big enough smooth lattice polygon, you can sort of like, there'll be a copy of that inside. And similarly, like for toric threefolds, there's a nice paper, and now I don't have the reference in front of me, unfortunately. I think it's Maserati, I forget the other names, where they like have a very small polytope that corresponds to a singular threefold. And so if you take that very small polytope, any 3D polytope containing that one is going to have, we could check that for that one, it has just the right number of points. And, using Macaulay too, we could check that it doesn't have the Terracini matroid property. And then any polytope containing that one is also going to fail to have the Terracini matroid property. So for toric threefolds as well, right? Uh, the the defective toric threefolds, I think, are rare, but toric threefolds with defective projections are plentiful. So you don't expect this Terracini matroid property to hold for toric threefolds. And so I think actually I'm going to end the talk there a little early. Yeah, I'll take questions or.
People might react first with their Zoom applause.
Thank you.
Questions for Jessica? Feel free to unmute yourself and ask away. I have one, just maybe a more simple question. If I have a toric variety embedded by a complete linear series, and I think of the sections as lattice points in a polytope,
Mhm.
should I be able to see the matroid I get from that? Are they just subsets, the maximal independent sets are subsets that span full dimensional polytopes? Is my intuition?
Uh, do they have to, are they exactly the ones that span full dimensional polytopes? Maybe. I mean, there'll be the lattice points among which there are no like homogeneous relations. And is that equivalent?
That was my question. In your example, it seemed to work, but I didn't know whether it
Yeah,
generalized.
I don't know. I'm not sure. Yeah. But it's weird. I mean, I think that like for the most part, if you're in algebraic geometry and you care about like intrinsic properties of a variety, you're not going to care about the algebraic matroid. It's like very extrinsic, right? It's not just like it depends on the embedding, it depends on like the coordinates in the embedding. Like so even just taking a linear change of coordinates is going to really change the algebraic matroid. And taking a general linear change of coordinates in general, I think will just give you a uniform matroid. And so like you don't know anything. It doesn't really tell you much at all.
Yeah, no,
So is there a most special matroid
Is what? Sorry?
of a variety? That would be a natural question. Sorry?
Oh, yeah. So like if you take a variety, what's the sort of furthest from uniform matroid you could give it?
Yeah. What's the minimal matroid?
Oh, that's a good question. I don't know. I don't
It's a
know.
little bit close to the question of um, uh, order normalizations, right?
Hmm. Yeah.
finding simple ones.